Hello again, everyone. So hopefully you have watched the introductory video on information processing and decision under uncertainty. So what I propose now to you is to discuss some additional details which are not necessary to understand the general framing of the problem of decision under uncertainty, but which nonetheless might be interesting for some of you. So it's more to give you some extra perspective on some more technical details which will be used in practice to process information and to deal with actual problems. So it's for you to have some extra information on some specific topics. So we are going to be discussing a bit on the definitions and the interpretation of probability, a little bit on risk, a little bit on solving more complex problems and seeing what are the mathematical difficulties of solving those problems, and also on some elements very superficial, but the general, the guiding lines for machine learning and building models. So I propose to you this short presentation. So let's start with probability. Probability, we've seen that it's going to be a measure, so a number we are going to put on different outcomes. So it might be an infinite number of outcomes, but still it's going to be used to weigh how likely are those different outcomes relative to one another. And this measure essentially is going to help us deal with both uncertainty and knowledge. So I'm not going to go too deep into what is uncertainty and what is knowledge, which would lead us to maybe too philosophical discussions, but still I'm going to give you the few interpretation of probability that people usually use. So you have the classical interpretation, you have the frequentist interpretation, and you have the subjective interpretation. So for the classical one, you are going to count the numbers of issues which are favorable to a given event that you're considering, and you're going to divide over the number of possible issues and equally possible issues actually. So it works well for the example of the dice. So if I want to know the probability of getting, for example, figure 1, then I'm going to do 1 over the total number of equally possible outcomes, which in the case of the dice is 6. So here it's pretty simple. So this definition is quite straightforward to understand, but it is mostly reserved for cases where we might count those equally possible issues. So the second interpretation, which is the more current one, let's say, so this one is going to be the frequentist interpretation, and this is very likely the one you're more used to based on the mathematical class you've been taking in high school, for example. So in that case, the probability to have a certain event is going to be the number of times, if we repeat an experiment over and over and over, it's going to be the number of times we observe that event E is true over the total number of trials. So if I flip a coin, on average, if I do it 100 times, 1,000 times, 10,000 times, normally on average I'm going to be 50% tails and 50% heads, and that probability in that sense corresponds to what I would expect as a ratio if I repeated the operation again and again and again. So that's the general in the common interpretation in the population. When you talk about probability, usually you mention that. On whole the video, we discussed about processing information and making decisions under uncertainty. What actually I was more inclined to using is the last one, what we would call the subjective interpretation or the Bayesian interpretation. So in that interpretation, I am more or less free to distribute the weight on the different outcome as I see fit. Now that might sound weird. Now we're talking about degrees of belief, so I believe that all those outcomes are equally probable. That might seem weird and very subjective in the sense that every people is going to come up with different values for different things. But actually you would have rules to put values which corresponds to the data. So if you put different probabilities for the different outcomes and your dice is fair, and if you compare it to what you would get with running trials over and over again, so if you do that, you would you would see differences between both those interpretations, and that's not good. So subjective definition of probability is actually going to be based on using data also. But in the end, in that interpretation, there's a more direct connection to what we know, what we believe. So if I take the example of the unbalanced dice again, if I know that the 6th figure is more likely to happen, then probably I'm going to attribute a higher weight to that probability value. So that's some ideas about what probability actually can be used to represent. So now let's speak a bit about risk. So we did not mention risk that much. What we mentioned was that we were dealing with uncertainty in solving problems, and that to come up with decisions, we had to consider two branches of tools, basically. So probability theory on the one side and utility theory on the other hand. So that means what is my do I like the consequences of certain consequences that might occur? So you have probability theory on the one side, utility theory on the other side, and they basically make up decision theory. So if we want to introduce risk, what is risk? So risk is a complex concept, but essentially you could see it, and some author in risk analysis describe it as a list of different combination of scenario, probability of those scenarios, and some kind of value for the consequences. So essentially, this is what we discussed earlier, in the sense that those are going to be coupled with probability values and a value attached to the consequence. So the idea is that I'm going to list possible outcomes, and on each outcome I'm going to put a probability value and a consequence value, a utility value. Okay? And then, as we've seen on the example, I'm going to choose between different lotteries. So let's get back to the idea of lotteries to discuss risk. So if you remember that slide from the introductory presentation, so in that case, I had only two alternatives, okay? So alternative 1 and alternative 2. So either a cross on the plank or I cross on the bridge. But once I made my decision, I'm not still sure of what will happen. So if I cross on the plank, I might get wet with probability P1, and I might arrive early and be happy with probability P2. So at the time I select my lottery, there's still uncertainty. And the idea is going to be selecting one lottery or the other. And this is what we might list as a quantification of risk. So an ensemble of scenarios, probabilities, and consequences. But we can basically see it as a lottery, okay? So that's a combination of probabilities and consequences, okay? So here there's only two scenarios, 1 and 2, and there's probability P1, probability P2, and consequences attached to scenario 1 and attached to scenario 2. But then the next step in picking actually the lottery is going to depend on our attitude toward risk. So when I mean attitude, I mean an element of choice. So that means that in that case, there's no right answer actually. There's no right solution. It's going to depend on what people prefer. So if you don't care much about getting wet, or if you it's a bit different than that. If you if the probability of you getting wet is not so important to you, then you might select that scenario. So let me frame it differently. Or let it look in the sense of, let us see what the solutions could be to pick lotteries. So one way to pick a lottery would be, let's pick the lottery which on average gives me the best results. And that's a possibility. The other solution would be, I don't like risk very much. I'm kind of risk adverse. So I don't care that much about what happens on average. I prefer to be sure that the worst consequence is not going to happen to me. So that's a different way to pick a lottery among different possible lotteries. But that's going to depend on the attitude of the person. You might have risk seeker who don't care if they suffer heavy consequences, or you might have risk adverse people. So risk adverse people would be more willing, even if on average they don't perform very good, but they are more willing to pick a lottery. So that's to say a set of possible scenarios which do not include a very heavy loss, or include that very heavy loss with very, very small probability. So there's no right answer to picking a lottery. It depends on our attitude toward risk. And that's essentially a part of the decision and the uncertainty problem. Because once we've framed the problem and once we've described all the different lotteries, there's going to be a choice to pick a rule to pick the different lotteries. And that depends on attitude toward risks. Now we've talked about attitude toward risk. So let's take a look at how to solve more realistic and complex decision problem. And let's say a few words about mathematical complexity. So we've seen that one part of the problem was what I call the framing, so that is coming with the different possible states of the world, attributing different probability values to each of them, and coming with a list of our possible action and their possible consequences in different states of the world. So essentially, that matrix representation is a conceptual tool, is a simplified way of representing the problem, because in many cases you might have a large number, a large space of possible outcome and a large space of possible alternative. And in some case, you might have continuous action space. So that is to say, you can choose a value in a continuum of different alternatives. So let's say I'm designing a bridge and I want to pick the width of the bridge structure. So this quantity is going to be a continuous quantity. So I have to pick among a set of infinitely many possible alternatives. So the dimension of this state of the world, of the state space and of the action space, could be very, very large. So here we run into the problem of algorithmic complexity. So this is very good to kind of think of the framing of the problem, but then when you're dealing with real problems, you're going to have to make simplification and to deal with algorithmic complexity. So here you have the general idea to understand the problem, and then you have some ideas of how complex the problem could get. So if you have a continuous action space, when you're looking for the best solution, you're going to be navigating a continuous space, as I said. When you have a discrete set of alternatives, you are going to be wandering in lists or tree to come up with the best action, which is going to correspond to a given lottery. And then, so that's one complexity, and then there's another complexity. So in many real world problems, what you will have is you will not have a single decision, but you will have a sequence of different decisions to make. So when you think of an autonomous car, when you think of a robot moving in space, it is not going to be making just one decision, it's going to be making a series of decisions in time. So here it increases again the dimension of the sample space and of the action space. So you're going to be able to take different actions at different instants of time. So here the problem becomes very complex, and that's where we will have to think about algorithmic complexity and finding solution to those complex problems, heuristics to help us look inside trees or find solution rapidly. When we're talking about different decision in time, we're usually talking about the policy, so how to behave in certain states of the world, given what we know our action might provoke. And less technical details, but that would be the contents of a full machine learning course, but I want to give you some details since we've talked about processing information, and those details concern the fact of building models, of selecting models, of training models, of seeing how those models might be used to synthesize the information, the data we have, and then to make predictions. So the idea is just to discuss a few general concepts. So first, what you will need to consider is what are you actually trying to accomplish? What is your objective? So there's two different, let's say, types of method. One is unsupervised learning and the other one is supervised learning. In supervised learning, which would correspond more to that case, what you do is that basically you're trying to build a model which will give you a value of interest, so let's call it y. So you are based on your knowledge of x, you're trying to predict y. And to train your model, you're trying to select the candidate function f here, which gives you the best fit between the points you actually observe, which would be x in the space x, and f of x, which would be the red curve that you have here. So that would be the training of your model. So that's supervised learning. So you have two types of supervised learning. You have regression and you have classification. So regression is going to be when you're interested in continuous outcome like this. So y here is a continuous outcome, and classification is going to be interested with discrete outcomes. So am I in state 1, in state 0, in state 2, in state 3, or in different possible discrete state, and I'm trying to see what states I am based on what I know of my parameter here. So that's supervised learning. You have unsupervised learning. Unsupervised learning would be I'm trying to find models to describe my data. So that might correspond, for example, more to that second case here, which would be, for example, the fitting of that distribution, of that two-dimension distribution here. So here I'm studying how my data are arranged in space, and I might use that either to make prediction or to get some information out of the data. So that would be unsupervised learning. So the first step is trying to see what we're trying to accomplish. And then the second step in building our model is making some choices. So choice of what function, of what candidate function we're going to look into, because we're not going to be able to look at all possible candidate functions. So we have to select a few ones. So the best fit function here, or the best fit distribution here. So we have essentially two choices. So we either go with parametric or we go with non-parametric. So with parametric definitions, what we will do is that we will propose a form for the function out of some dictionary. We can do combination and some different small functions, small structural functions. So that's going to be the case of linear models. That's going to be the case of non-linear model. That's going to be the case of neural networks, which are based on basis function and on some specific form, functional form that you will sum up to get a given results. Or you would have what we would call non-parametric models. The non-parametric model generally will be based more on the data itself. So you're going to predict what happens quite close to a data point based on the most local data point, or an arrangement of the different local data points. So you would have kernel methods, you would have SVMs, you have a whole lot of different possibilities, but usually now you're not based on the functional form that you're trying to fit. You are more based on trying to understand what happens locally in space, okay? So you have a whole lot of different methods and different possibilities, but essentially it's about picking a candidate function and then training it using some inference principle, some learning principle. So the last point before I conclude on this additional video is going to be the idea of generalization and prediction. Essentially what happens when you're training a model is that you will use it to predict points you haven't seen, okay? Because the data you have is the data you have. What you want is to make prediction for points you haven't seen. So either further in time or for a different value that you have not observed. And that is going to be what you make as a prediction is going to depend on what you assume, and you are going to be willing to avoid some phenomenon, which is overfitting. So overfitting means that if I'm trying to fit extremely well my model to the data set, I can always do that. I can always choose a model which goes through each point. But the problem is that if I use that model, it's very unlikely that it would give me good prediction in a true situation, because reality is probably more complex. I'm probably missing things. So it's not very good to fit the model very smoothly, because then my predictions are going to be of poor quality. So you have kind of a trade-off to reach between model complexity and quality of prediction. So if you make your model too simple, probably you're going to miss a lot of things, so your prediction is not going to be that good. But if you make your model too complex also, maybe it's going to be very good on your data set, but it's not going to be good to make actual prediction once you go out of the values and the data set you have. So thank you for your attention on both those videos. I hope you've learned something. Some things probably you knew already, but that's to give you a general perspective, both on the simple part and the conceptual framing part of the problem, and on some additional technical details. So if you have questions and if you want to discuss further, of course, I'm very open to it. And also I'm very open to comments and suggestion if you liked both those videos. Thank you and see you.